Yeah, that makes sense. So Peter asked me to stand in for him, and so here we are. To try to avoid utter confusion, I'm going to say only a couple of things for IBM, but I'm not going to use slides. If you want to hear the IBM position on ARM, there is the talk that Peter and I gave in London in June that is recorded on YouTube. You can listen to the first 15 minutes of that, and you have IBM and Red Hat's position on ARM and what things are coming there. The cliff notes are we're supporting Ceph ARM clients starting with the 8.1 release in June, and we're working to bring the clusters as well with the next release, which will be 9.0. There are lots more details, but let's focus on the performance data here instead of being too vendory about commercial offerings. So, Ampere. Ampere has been focusing on performance per watt where it comes to Ceph. And these are their core questions. What is it, and why should we care? And Rama and Peter very kindly provided the answer. So they're measuring IOPs per watt, and they're trying to measure the energy efficiency of an IOPS operation, of a single IOP, essentially, and compete on that as a metric. Which is interesting and novel. The higher IOPS watt is desirable, it's better. And obviously, if you are into building data centers, you know that one limiting factor for many data center build-outs is power to the rack. And there are very power-hungry things that are being deployed right now, so you cannot really populate a full rack with the kind of draws that some hardware, we're thinking more of GPUs here, pulls. So this is topical not just in terms of saving electricity or saving the cost of electricity or saving the environment. It's topical in terms of being able to fill your racks fully with the standard power delivery. How have they been measuring this? So the factors that go into this metric are essentially what type of medium do you have? Solid state tends to consume less than spinning Rust. The workload type, how much are you hammering the storage? Is it idle? Are you writing a lot? In fact, I will take back what I said about spinning Rust. Spinning Rust is very power efficient when it's idle. But when you start spinning up those things, then that's a different story. Block size is also a factor here. Obviously, if you are doing very large size IOPs, you're going to get fewer of those. So it throws the metric in a different direction. So you need to account for block size. And of course, as in everything Ceph, how you configured and integrated the cluster. So Ampere's focus here is the cost savings, the environmental sustainability, and also the fact that you can get more performance, what I was hinting at in terms of you can have more with the footprint that you can deploy. Ampere CPUs have a ridiculous number of cores. I think that's the technical term. So obviously, they foster packing more things in smaller space. So Ampere has been doing experiments with this kind of setup for a while, and you can find white papers on their site, and I think on Ceph.io, if I remember correctly, with their older platform, their older chipset, which was called Ultra, which actually is still called Ultra. You can power Ultra nodes on Microsoft Azure, I believe. But there is a newer one called Ampere 1. So the benchmarks that they wanted to share here today are about the comparison of the two. There is a footnote here to these things, which is I don't think from a Ceph point of view is so relevant, but just in terms of being transparent with the benchmark, they wanted to note that their ultra benchmarks were on Quincy, while the Ampere 1 benchmarks are on Squid. What else? They are on Ubuntu. One thing that's interesting is, well, obviously I was talking about the processor. So the processor on this cluster is an Ampere 1, which I believe means 192 cores. They have 8 SSDs per node, and this is a cluster of 3 nodes. So it's a fairly minimal configuration. They are doing the early steps of characterizing performance. They are not doing a massive build-out. They're using Ubuntu 24.04 as the OS, and their deployment is Squid containerized. I believe, oh yeah, the network is 100 gigs, and the storage is all solid state. Okay. So they filled about 20% of the cluster in terms of how far the benchmark went in terms of capacity. They had 3 hosts deploying 3 monitors, 2 managers, 24 OSDs, which is the interesting part, I think, and offering 4 pools. The configuration had 6,000 PGs. So what did they measure? Here is the comparison between the Ultra results that were released before and the Ampere 1 results. And now, I think there is one thing that's important to consider here, looking at the numbers, and it is that the Ultra cluster had 4 hosts, while the Ampere 1 had 3. So I think Peter and Rama make some statements later, well, where the numbers will not make sense if you're not aware of the size of the cluster. So keep that in mind. Nice thing so far here in terms of characterizing how it's working. They are not hitting any obvious bottleneck, at least at this scale. What they would like to see is some indication of saturation. So Rama has indicated that the next benchmark he will do will use at least 12 OSDs. And he wants to see a point where adding more OSDs does not increase I/O, and so essentially we're running out of some resource and discover the first bottleneck that way. But at 8 OSDs, he has no bottlenecks. It's still growing linearly very nicely. The comparison in the red box is what I was hinting at. So 4K IOPs, they're seeing 400,000 IOPs in the Ampere 1 and 200K with the Ultra. So their new chip is doing quite nicely there. I believe these configurations are replica 2. I think so. And the latency is increasing, but not horribly. So, so far so good. That was write performance. Now, read performance is even more linear. So it's very clean in that way. And you can see at the top on the right, the red columns, the performance improved, but it's slightly slower than writes. There is something there at, so Rama measures a 2x improvement when he normalizes everything for the writes, but for the reads, he is seeing only 1.8, and he thinks that there is something that needs to be figured out there. But the performance with incremental OSDs at this scale is going linearly, which is neat. No, so I should qualify the statement. So when you introduce a new architecture, like when IBM introduced power for Ceph, we have a power distribution because we're IBM. You discover very interesting bugs that come out of nowhere that are very platform specific. So this kind of test that Rama is doing with ARM is aiming to discover the same thing. He wants to do a sanity check and see that behavior is linear as expected, and it is. So the most obvious bottlenecks from ARM are not there at this scale. Now, as we ramp up, we're likely to see more. But at the small cluster scale, it's promising. There is no massive blunder that we need to be worried about. Now, going to the power consumption, here you can see there are 4 nodes on the left and 3 on the right, what I was pre-disclosing. So that's why the numbers look better on the Ampere one. The individual nodes consume more, but because they were able to achieve higher performance with 3 nodes than they used to with their older chipset with 4, they're actually posting an improvement in the power benchmark, not just in raw muscle. So that's a nice advance. And I think he has the numbers here, 400K IOPS with 1430 watts, and the older benchmark was 200K IOPS with 900 watts, but 4 nodes. All right. So on the back end, the chips are also different. The reason why the Ampere one is more efficient is that it is able to do more work out of a single box, having 192 cores instead of 64. I'm not familiar with their hardware lineup, but obviously their machines can take more than 8 drives. So they're trying to figure out how to. They're not a storage vendor, so they cannot call and say, I want 64 drives in the lab right now. They're working through that. But at this scale of benchmarking, it's quite interesting. And the results are that the Ultra was essentially, once everything is accounted for, was posting at 223 IOPS per watt, while the Ampere one is posting 285 IOPS per watt. I think it would be interesting if they made a comparison with Intel chips here, but the problem is it's really difficult to do this fairly. So I can see why they didn't do it. You would have to account for all sorts of variables to be able to make a meaningful statement between things that are so different. Usually my position is you can only compare dollar per dollar, right? I'm going to give you a budget, this many dollars to build one and this many dollars to build the other, and you go wild using the assumption of your specific platform. If instead you build the same thing on both platforms, the choices that you've made benefit one of the 2 vendors. So that's why benchmarks are usually referred to as lies, damn lies, and benchmarks, right? That's the core of the problem. So unfortunately, there is no fair way to do a comparison there. But still, if you want IOPS per IOPS and if you have a specific choice of hardware, you can run your own benchmark against that hardware and see where you're falling, right? How many watts does an IOP cost? Here the argument is essentially that you want to figure out the OpEx cost of your cluster, not just the capital cost of deploying it, which I absolutely agree with. And the fact that this metric is not something that is as widely used as it should be, which I think is an excellent call out. That is pretty much what I have. I don't know that I can answer questions because it's not really my company or my presentation, but this is what I understood from their presentation. Unfortunately, they couldn't be here in person. All right, that's it. Okay, thank you. I'm happy to discuss ARM, but off the record, because I cannot speak for Ampere to your questions.
Can I go with a open question? How strongly do you feel that coding with a low power consumption in mind makes sense?
Coding to low power consumption?
Yet, no, coding in a way that will enable low power consumption. So all those optimizations, maybe more parallelism instead of targeting for a stronger cores. How much do you think is there value in that?
I don't have a sense for it. I think that it's a good question. I don't have an immediate sense that it was going to be a huge difference. The last time that I looked at something like that, I wasn't doing it for performance reasons. I was doing it for side channel security reasons. I wanted to know where things were running, and I was trying to say, let's not run so many things that we're giving 10 side channels. Let's try to give only 5. But that, when you're doing security, you don't care about the price, right? I don't have a clear sense of how much of the processor you could idle to save. The most obvious target is to have single socket systems instead of 2 socket systems. So large core counts would help. That would kind of be my first thing to look at. How big is the difference? We would have to measure it. All right. Thank you. If you want to discuss more, I'm happy to stay, but I don't want to put my opinions on the Ampere talk. I can give you my opinions on ARM separately. Thank you so much for coming.